give us our keynote talk to almost close out the day. One more session after this. So Professor Gonzalez is a professor at Louisiana State University. Her research focuses on the detection of gravitational waves, working with the Laser Interferometer Gravitational Wave Observatory, LIGO. Professor Gonzalez was born and raised in Argentina, received her PhD from Syracuse University. Upon graduation, she worked with the MIT LIGO group and was a founding member of the LIGO scientific collaboration. She joined LSU in 2001, and in 2011 was elected as the LSE spokesperson, which she served in that position until 2017. In that time, in February 2016, she was able to be one of the 5 LIGO scientists present for the announcement of the first observation of direct gravitational wave in September 2015. She's a fellow of the Institute of Physics, American Physical Society, American Astronomical Society, and a member of the National Academy of Sciences and the American Academy of Arts and Sciences. Thank you very much, Gabby, as I know you've been called in the sessions that you've been joining so far. We're so delighted that you're here and talking to all of our teachers gathered in this main session. As a reminder to everybody in the audience that you should be navigated in Whova to the keynote with Gabriela Gonzalez session, and there should be a Q&A box there. I will moderate Q&A at the end of Gabby's talk. Please take it away.
Thank you. And thank you for inviting me. I admire teachers. So I'm very, very impressed with your work. And I was very glad to join one of them sessions, one of the earlier sessions today. So let me race through this because there's so much to talk about and so little time. First, let me tell you about Einstein's gravity, general relativity, which sounds very, very intimidating. I know I was intimidated when I first heard about it, but it's not that intimidating. The idea, Einstein's idea to explain gravity was to think about space-time, like a 3-dimensional grid with clocks in every corner, and that space-time is curved if we have masses, like this. So if we have a mass, it curves space-time, and then the other masses, all the masses in the universe will follow that curvature, will move because of that curvature, and that's why the Earth goes around the sun. So if we have two bodies, they're both curving and they're both following the curvature of each other, and that's how a satellite goes around the sun without needing a force of gravity. It's a curvature of space-time. And this theory had lots and lots of predictions, some that even surprised Einstein, like the existence of black holes. He didn't believe in black holes. Many people didn't believe in black holes. But now we know they exist. He didn't know that by the time he died, but they do exist. We know that they are born from the explosion of supernovas, of certain classes of supernovas of massive stars that leave behind a black hole or a neutron star. A neutron star is the most compact kind of stars, and these will be the 2 stars of this talk. There are stars like our sun die a quieter death, not the supernova explosion, but they end up also as a compact object, but quite a bit larger in radius as a white dwarf. These black holes are born of massive stars, so they have tens of solar masses, maybe 100 solar masses, not heavier than that. But you probably know that there are other very much heavier black holes at the center of galaxies. You might remember last year's Nobel Prize that was given for the theory and the observation of black holes. The observation of this black hole is not through, it doesn't emit any light, but one can see the other stars around it moving and reconstructing the position and the mass of that black hole. And that's what Andrea Ghez and Reinhard Genzel, Andrea Ghez in the US and Reinhard Genzel in Germany did, looking at stars in the center of our galaxy. And of course, I was very happy to see Andrea Ghez in 2020 after another Nobel Prize to another woman in 2018 or 19. Now, the black holes that are born from supernova explosions, we cannot see them because they're black, but we can see them because as things that happen around them. Because if they are, for example, in a binary system around another star, then there will be matter from this other star that is falling into the black hole. And that mass, those particles that are moving so fast, are emitting electromagnetic light. They emit light. Those are usually X-rays. So we call these observations of black holes X-ray black holes. Of course, it's not the black holes themselves that emit the X-rays, but we know the black holes are there because of these X-rays. And there are lots of satellites that look for these and have seen many of these. So we can see black holes even though they don't emit light. But with gravitational waves that are predicted by Einstein's theory, if we have two black holes or any two masses that will be orbiting around each other, like the Earth around the sun, then that motion produces motion of the curvature. And those ripples of space-time are the gravitational waves. So they are periodic waves of space-time produced by the motion of two masses. And those two masses produce these gravitational waves. These gravitational waves are going to take energy away from the system, which means that the two stars, the two objects, are going to get closer and closer together. That's according to Einstein's prediction. Newton would predict that they go around each other forever. For two black holes, and this is a numerical relativity simulation, Einstein's equations are they are beautiful equations, but hugely complicated, so they can be solved on computers. And this is a simulation showing the curvature of space-time around these two black holes. The movie is slowing down, even though the black holes are moving faster and faster. The two black holes end up fusing into a single black hole. I like to say, being from Argentina, that they are dancing a tango and end up in an embrace. And that last black hole, that final black hole, is still rotating, but not producing gravitational waves, because according to Einstein, anything that's spherical, that's perfectly spherical, does not produce gravitational waves. There has to be something non-spherical about the system. Like me, I'm producing gravitational waves. The two black holes were producing gravitational waves, but the final black hole is not. So those gravitational waves were periodic as the black holes were rotating around each other. But then as they were moving faster and faster, then the gravitational wave is larger in amplitude and frequency. And then after the merger, there's a little ring down and they disappear. Now, what is this wave, this ripple? We said it's a ripple of space-time, which means that the distances are changing. The sizes of objects are changing too, although in that case, they're fighting against other forces. And that's what we can measure with a Michelson interferometer. A Michelson interferometer, you might remember, is a source of light that is divided into orthogonal arms, and then they bounce up on mirrors at the end. The mirrors here are very far away, and then they come back, and we look at the interference of those light beams. And if this distance is equal to this distance, then we know that at the output, the waves are going to cancel each other. There is no light at the output. But if this distance is changing with respect to this distance, then there will be some light at the output. So just putting a photocell at the output, we can see how much light there is. And if there is light that's more and less and more and less, we can say, well, there seems to be a gravitational wave. Now, I'm showing you pictures of the two observatories in the US, the two LIGO detectors in the US, and they are 4 kilometers long in Hanford, Washington, and in Livingston, Louisiana. Why so long? Because it turns out that the longer the distance we measure, the larger the change. What is constant, according to the amplitude of the gravitational waves, is how much the distance changes divided by the distance we are measuring. It's a fractional change. And the prediction again was that that fractional change was going to be very, very, very small. Some people thought impossible to measure because gravity is a very weak force, which means that the constant, Newton's constant in this theory of gravity, there's a speed of light, the amplitudes are really, really small. But as you know, we did measure gravitational waves. We did that because we used a lot of technology. The light beams are traveling in vacuum, protected by a concrete enclosure. The mirrors at the end are hanging in quadruple pendulums, hanging from an active seismic isolation system. All of that is enclosed in vacuum. We use a powerful laser. We use state-of-the-art, heavy, very large mirrors. And we don't have a simple Michelson interferometer. We actually have, we make the light go back and forth in the arms. We have optical cavities. We have to control all the mirrors. So this is an engineering marvel. And with all of this, we get at the output, at this photodetector, in general, noise. And we built initial LIGO detectors. We are operating now a second generation of gravitational wave detectors to make this noise due to the motion of the masses and the Brownian motion and the quantum noise of the light and a lot of other things. We make that noise smaller and smaller and smaller to make the detector more sensitive. The LIGO detectors are not the only ones in the world. We have taken data and operated with a Virgo detector, 3 kilometers long in Italy. We developed technology in a 600-meter detector, Geo 600 in Germany. We will begin taking data, hopefully next year, with a Japanese detector called Kagra, 3 kilometers underground. And there is another observatory being built, 4 kilometers long in India. And doing all of this, having all these observatories working together, help us triangulate the signals when we have 3 or more detectors operating to know where the signals come from. So I told you how we detected. This is the first thing that we detected. And this, it makes me cry sometimes seeing it and remembering the first time we saw this. I'm plotting here the signal that we see in the photocell, the amount of light in the photocell, in blue at Livingston and in orange in Hanford, 3,000 kilometers away. And this is in general what we see is noise, and this is calibrated in strain, which is the ratio of change in distance to distance. And that's a small number, 10 to the minus 21. That's 4,000ths of a proton diameter compared with the 4 kilometers between the corner and the end stations. It's a number almost impossible to imagine, but here you can see it measured. And in general, what we see is noise that is different in Hanford and Livingston. But here we saw what is expected to be seen from a coalescence of black holes. We see a signal that grows up in amplitude and frequency and then decays in a fraction of a second. From the frequency, we could tell that these were black holes of about 30 solar masses each. From the amplitude, we could tell that they were 1 billion light years away, more than 1 billion light years away. So this was huge. This was huge, and it happened September 14, 2015. Something that we like to say is that this is like the music of the universe. And we put this in sound because we can put this signal in a speaker. We digitize it and put it in a speaker. Of course, these are not sound waves, they're gravitational waves, but we also like this visual way of looking at the waves where this is time, this is frequency of the wave. And as we can see here, the frequency gets higher and higher. So the frequency goes from tens of hertz to about 200 hertz. and the brightness is the amplitude. This is a time frequency spectrogram, and we love this. So this is what it sounds like. Now, what we do is put it on a speaker, and this is, for some reason, it's not very loud. And I'm not sure you can, let me make sure that you can hear it. So you might want to increase the volume on your computer. So what I'm going to make you listen first is the sound of this twice. So we only saw one wave, but it's going to appear twice. Now, you heard it first at a lower pitch, and that's a real pitch. These are very low frequencies, so they don't sound very nice to the ear. So we added 400 hertz to this so that they can sound nicer. And that's, again, the original pitch and then the increased pitch. Did you hear it? That was the real sound. And this is the nicer sound. This, of course, was huge, huge news. I had the honor of being one of the people announcing this detection February 11, 2016, which was also the first day that the International Day of Women and Girls in Science was celebrated. So that was a very, very nice coincidence, given that the press conference was presided by another woman, Franz Cordova, the director of the NSF at the time. And in 2017, it earned the Nobel Prize. And something that we're very happy to see is that the Nobel Prize was awarded to Ray Wise, Kip Thorne, two scientists that had proposed this project in the 70s, Barry Barish, who had been an executive director of the project at a difficult time, and he made it go. But the affiliation was presented as LIGO-Virgo collaboration, because we were all working together for many, many years to do this. I'm looking at these Nobel Prizes and the previous, except Andrea didn't look like that, but they kind of all look the same. And I want to say that you shouldn't think about Nobel Prizes and physicists in general as gray-haired or no-haired men. At the time they did their best work, they were a lot younger. This was Einstein at the time. He developed the theory of general relativity, which was his last big accomplishment. He had other accomplishments before. This was Ray Wise and Kip Thorne in the 70s and 80s when they developed this project. And the people working on this are of all kinds, of all cultures. We are all around the world. At the time of the announcement, this was our group at LSU. And you can see that we don't look like gray-haired men. They are the young people are the people doing the science, and that's how you should imagine physicists. Okay, let me tell you the news. There have been lots and lots of news since that first detection. Remember, that first detection was in 2015, September 2015. That was this one. It still has a record of largest amplitude. In this spectrogram, it would be the brightest. But we have in 2017, we published a catalog of 2 observing runs that we had done, and there were 11 detections, 10 different detections of black holes of different kinds, and 1 detection of a collision of 2 neutron stars. So that was very different. Notice that these are all half a second. This spectrogram shows tenths of seconds. And that's because we can see many, many, many orbits in the frequency, in the sensitive frequency band of our detector before the neutron stars coalesce. The black holes, because they're bigger, they coalesce at lower frequencies, like hundreds of hertz. The neutron stars that are smaller, about a solar mass, 1.3 solar masses, 1.3, 1.4, they coalesce at thousands of cycles, thousands of hertz. So this was also big, big news because It was also relatively close in astronomical standards, and two black holes do not produce electromagnetic waves, but two neutron stars should, and they did. In fact, it was detected at the same time. The coalescence in the LIGO detectors, again, putting it in music, was detected in coincidence slightly before, 2 seconds before, a gamma ray burst, detected by the Fermi satellite. And that's because the collision of the neutron stars produced this gamma ray burst. These signals travel 130 million years and arrived to Earth less than 2 seconds apart. So that was proof that gravitational waves travel at the speed of light. And the region could be very well localized because we were taking data with Virgo. People looked at the galaxies and they found a very bright spot. And we could tell the full story of these two neutron stars. There were the two neutron stars that were dancing the tango, although for quite a bit. And then they coalesced and produced the gamma ray burst, and then they produced light in the more isotopic medium, and then they produced X-rays that 10 days later produced X-rays and radio waves. And all of these things were observed. It was amazing. This is now one of the best astronomical events studied in the history of astronomy. Now, that was not all. That was until 2017. These were our first two observing runs. These numbers represent a way of measuring sensitivity. In 2019, we started with Virgo, a third observing run, and we took data for almost a year. We had to stop because of COVID in March of 2020. And we, as I told you, we saw 3 binary black holes in the first observing run, 7 more in the second observing run, and this one binary neutron star. We had public alerts. We had an app you could get in your phone to receive public alerts, and there were 56 alerts during this third observing run. And we have published the discoveries in the first part of that third observing run. This is what we knew from that first catalog. This was that first gravitational wave. That was that first binary neutron star emission. This is what we have from this second catalog with the first half. We still have 5 more months to analyze. These were the first 6 months. And you can see we are filling these. These yellow points are the masses of neutron stars that were known from radio astronomy. The purple circles are the black holes, the masses of black holes that were known from X-rays, the X-ray black holes. The blue ones are all the ones, all binary systems that we have seen with LIGO and Virgo. So there are some special events. Apart from that first one and that first neutron star, there was another neutron star merger, 1904-25, that's a date. That was farther away, so there were no electromagnetic counterparts, but there it is. And another, this was the first binary neutron star detection. This was the second one. There was a detection of the merger of a black hole and an object that we don't know. It's a bit too heavy to be a neutron star. It's a bit too light to be a black hole. So we cannot tell one way or the other. There's no physics that doesn't allow black holes this small. There's no physics that doesn't allow neutron stars not that big, but almost that big. But we are gathering new information now with this. We also saw the heaviest black hole that ended up at more than 140 solar masses. And this original black hole of 85 solar masses is so heavy that we think that it was not produced by the explosion of a supernova, but maybe by the merger of 2 other black holes. So again, we're breaking new territory. And just a few weeks ago, we published the latest discovery, which is 2 observations of neutron star and black holes. So this is not in the mass gap. It is a real neutron star with a typical neutron star mass and a black hole. But we saw two of these and 10 days apart. These were amazing. These are both from January of 2020. So these are neutron stars and black holes, and the neutron star is getting distorted as it gets into the black hole, but we have not seen electromagnetic counterparts. So lots and lots and lots of discoveries, but these are not all. Now, before telling you about the future, I wanted to tell you about some resources, educational resources. There are now two. There used to be just one science education center next to the Livingston Observatory. There is a LIGO exploration center being built next to the Hanford Observatory. So now you are probably close to one or the other, relatively close, but of course there are virtual visits you can do. And we have educational resources at these sites. I can share these slides and you can get these links, but they are all at LIGO.org, and you can travel from there. So on LIGO.org, we have all kinds of resources for scientists and teachers. So let me finish telling you a bit about the future. We said that we took data in the third observing run. We were planning to start the second observing run late this year, early next year. We probably won't start until middle of next year, but we will start with CAGRA, not just with Virgo. So we will be 4 detectors working together. We are 3 collaborations all working together. And we already have upgrades to do to improve the sensitivity of the detectors and see more and more events farther away, hopefully with counterparts. And we are not just looking for these dances of binary systems, we're also looking for supernova explosions. We are looking for unresolved signals that look like noise, but it's not noise, it's astrophysical noise. And we are looking for periodic signals produced by rotating stars in our galaxy. And you can help us. You can get involved in the search of gravitational waves, going to Einstein at home to help us look for these periodic waves, or going to Gravity Spy to help us identify things that are not gravitational waves, but are transients or glitches in our data. So there's a lot happening. There's a lot more happening in the next few years. And we are very, very glad to talk with teachers and students about all of this. I hope you have questions for me because I love questions too.
Fantastic. Thank you so much, Gabby. I'm going to do the virtual round of applause. Thank you for that great talk. I do have questions. They're coming in via the Q&A. So I will read out a couple to you and we'll see how much we have time for. I will tell everybody that we're okay running a little bit late into the next session. We might not get to all the questions, in which case maybe Gabby can go into Huva and answer some in chat, but I'll start reading them out. So the first is actually kind of a combo from 2 of our teachers, Michael and Celestina, about the speed of gravitational waves and specifically how that compares to the speed of light, and then specifically how they arrived prior to the Fermi satellite observation.
Right, let me go to that slide. Yes. So this one, let me get, the gamma ray burst happened after the collision of the neutron stars. So people knew it had to come after. So this is the collision, this is the gamma ray burst. This had to come after that, and physicists, astrophysicists were surprised about how small that time was, 2 seconds. But again, this is 2 seconds compared with 130 million light years. So the prediction of Einstein's theory has the speed of light in there and says that the gravitational waves travel at the speed of light. Alternative theories say they travel slower. Here, it shows that they travel at the speed of light with an amazing precision.
Very cool. And thanks for sharing that audio again. I really love this one. So the next question that I really liked from Christian, one of our teachers, if we could experience gravitational waves on a kind of a human scale, what would it actually feel like if you can convert it into some kind of sensation? And specifically, it was, is it going to be very climactic or maybe hard to notice, which I appreciated that detail.
It is very, very hard to notice. That's why we have to use so much technology to discover these gravitational waves. It is a fractional change, and it would mean that our height and width would be changing by a part in 10 to the 21. So we don't measure our height or our width with that precision. We wouldn't notice it at all. In fact, there were earlier experiments trying to measure vibrations of aluminum bars, and even using a 1-ton mass, they couldn't quite get the precision needed for these gravitational waves.
Interesting. The next question is about the detection and then the Nobel Prize that came in from Zara Hazari, the fearless leader of our project, and was upvoted. So note for folks, you can upvote in the Q&A tab. So what is your view? Is it problematic that certain individuals get primary recognition for these large scientific collaborations?
It is, although many people are working around it. There are many talks in conferences, and those are usually given by the younger people who, again, are the ones doing the work. So you have to think about scientists as the young people doing the work. They are the ones. But we, the more senior people, are trying to balance invitations to conferences and writing, especially in writing letters. Much of the careers of people is done through letters, and the more the community expands, then the more we can promote each other. And we try to organize that. But it is a change of culture from small science to big science. It happened already in particle physics, but now it's happening in gravity and astronomy.
Awesome. The next one that was upvoted is hopefully simple, and it is whether they can get a copy of your presentation. Would you be able to share the slides with us?
Yes, of course.
Okay, and then we will get them to you via Huba or another platform, everyone.
And
don't worry.
I also, well, here it is. I also have my email in this last slide if anybody wants to answer questions I didn't hear.
Fantastic. I will ask you for a copy and get that out to everybody. So don't everybody ask the presentation question, because I will take care of that for you. But thank you very much, Gabby, for being willing to answer other questions. The next I have is, how would the gravitational wave look different? What would be the difference if the two black holes had different masses? Can you talk a little bit about what the gravitational wave looks like then?
And we do have systems like the Neutron Star black hole system that has very different masses, a ratio of almost 10. And it doesn't look that different. It has different frequencies, but the waveform does not look as different as you would think. It does vary a lot if the stars are spinning. If the stars are spinning, and they usually are, most of the stars spin, then they would produce a modulation of the waveform. But we have, our results seem to indicate that there's very little modulation, so that the spins seem to be either very low or canceling each other. So that's still something that astrophysicists are trying to figure out.
Cool, it's always great to have a question, and we're excited for the teachers to be able to bring so much of this back to their students, and we're still figuring it out answer is one of my favorite for that reason, right? We need.
That's right. Yes, every discovery has brought more questions.
Exactly. Okay, so I think we've got time for one or two more, and then I will point you to the other questions that you can answer. The next is from Michael and upvoted 3 times. Do you see any potential for new applications where gravitational waves are used as a new form of communication, like radios or TV?
Well, just like they are very difficult to detect, they are also very difficult to produce. So you would have to manipulate black holes or objects like black holes or neutron stars or things that are moving that fast, that close to the speed of light. That first detection had those black holes moving at half the speed of light when they emerged. So I really don't see gravitational waves being any easier than electromagnetic waves. They have some advantages because the effect is so small that most of the universe is transparent to gravitational waves. We saw the gravitational waves almost exactly like they were produced, and that's how we can know so much about the origin. But then that makes them very difficult to detect and produce.
Is there active research to produce a gravitational wave? Is that something that's being studied?
Well, there have been lots of calculations done on what would you need to produce gravitational waves, and there's no way.
There's no way. Okay. So
well, one should never say there's no way, but we can produce amplitudes of 10 to the minus 40, and we have been able to detect 10 to the minus 21. So we are about 20 orders of magnitude too rough.
And I'm going to call this the last question, Gabby, because otherwise I think we could go forever. And I love all the physics that we're covering. This is really fun. And again, we're excited for teachers being able to take this back. So the last one that they can share with their students is around the ability of gravitational waves to see beyond the cosmic microwave background. How would that even happen? And wouldn't the signal be too weak once it reaches us?
Yes, so the early universe produced a gravitational wave cosmic background, just like the microwave, the cosmic microwave background. But this gravitational wave background was produced earlier, much, much earlier. So we could know about the early universe. But all the calculations, of course, there are lots of cosmologies, different cosmologies, but all the theories predict much amplitudes that are so small that we wouldn't be able to detect those with our LIGO detectors or with space detectors that are being built right now. However, there is an imprint of that early gravitational wave background on the plasma that produces that cosmic microwave background. So there are many experiments, and they're getting more and more sensitive, that measure the polarization of those cosmic microwaves. And that would tell us about the gravitational waves that produce that polarization. So I expect that discovery to happen really soon.
Excellent. Stay tuned, everybody, for the future answer to that still being worked on question.